how many factors are considered when making a potassium recommendation. And then I just listed the factors, and I'll share those findings with you. Here I have all of the states listed at the bottom, and these are the 30 states that provided information of the 31 that were surveyed. And here's the frequency. This is the number of factors that were considered in potassium recommendations for each state. And you can see that about an average of 3 factors were considered when making a potassium recommendation. Let me show you what those primary factors were. You can tell in the U.S. we are very much a soil test-based recommendation system for making K. All of our states use soil tests as the basis. Some other factors that were very popular were yield goal. This is the intended or target yield that farmers have for the next crops that are grown, the next seasons. Nutrient removal was considered in only 10 of the 30, and that's an important consideration for keeping track of nutrient budgets, making sure that nutrients are replaced when they're removed. And then I want to show a few factors that, and I'll highlight these, that are associated with mineralogy. The cation exchange capacity, in some recommendation systems, soil association. This is basically which soils group together in the landscape in various areas. Soil texture was part of that as well in some states, and soil type. But you can see that of the factors that are considered, things that deal with mineralogy are not well considered in most recommendations. CEC is probably the best proxy for soil mineralogy that we have, and even CEC is not a major factor in altering potassium target levels in the soil or altering rates. So in general, in the U.S., we know that soil mineralogy is important, but it is very difficult, and we'll see why, it is very difficult to incorporate it well and completely into the recommendations that we make. So moving on then, just talking a little bit about the dominant minerals in the Midwest. The ones that are of most concern to us are the phyllosilicates, and these are the soil minerals with a layer structure. We typically associate this with the clay size fraction, the smallest fraction, smallest size fraction that we deal with in soils. However, I'm going to show you something later that will show that these minerals can exist in larger size fractions like the sand fraction, and I think this is an important consideration for us as we move forward. There are some basic types, and I just want to show that in the U.S. we deal pretty much with the bottom type, and these phyllosilicates are composed of different layers, and in Brazil in particular, I think you deal primarily with this one-to-one layer structure that we see with kaolinites. In the one-to-one layer we have what we call a tetrahedral sheet, which is basically a silicon atom that's surrounded by 4 oxygen atoms. You can see 3 of those here, and that forms these tetrahedron. Just below that sheet and attached to it is an octahedral sheet, where we typically have aluminums or sometimes iron or other metals will substitute for aluminum. And this is an octahedral coordination with oxygens and hydroxyls. So there are 6 of those oxygens or hydroxyls, OHs, surrounding that aluminum cation. So when you have one tetrahedral sheet to one octahedral sheet, that's called a one-to-one type of clay mineral. In the U.S., we basically deal with 2-to-1 clay minerals, where we have 2 of these tetrahedral sheets, one on the top and one at the bottom, and we have an octahedral sheet in the middle. So that's an important difference in terms of the reactivity in soils. These 2-to-1 layers have a bit different reaction with potassium than the 1-to-1s. And so I'll focus primarily on the 2-to-1s and how they affect our reaction to potassium management. Here we have the structure of a mica. Also, the illite this is kind of a not a very well-defined mineral, but it's part of the mica group. It's an important mineral, as we'll see later. But here we have the 2-to-1 structure again on the top, and we can see that in between these layers or these sheets of minerals, we can get potassium that becomes a structural component of that mineral. It's fixed in the inner layers, and it's held there by electrostatic charges. So the potassium is positively charged cation, and these sheets carry a net negative charge. So then the positive and negative charges help hold that potassium in place, and also the arrangement of the atoms makes it a structurally good place for potassium to bond. This is an example of illite, and we will see that mica in general can layer to weather to form other minerals. And so here we have mica that we just showed, and that can, over time, these bonds between these layers can break. They weaken through both chemical and physical forces that act upon them. And as these layers start to, those bonds start to break, other ions can move in. So here we have potassium that has no water around it, and we can begin to get things like calcium, magnesium, sodium that do have water molecules surrounding them. That helps create a greater distance between the two individual layers of the mineral. Over time, as these micas continue to weather, these edges can start to break apart, and these other ions move in, and that eventually can lead to the formation of a new mineral, in this case vermiculite. So the important thing here is when we have minerals in the soils, they can weather to form other minerals, and this can happen at very short ranges of atomic distances, and I'll show the importance of that. So here we have vermiculites and smectites. They're both what we call swelling minerals, and it's because they do have these cations that form or bond in the inner layer between the mineral layers, and have waters around them, and that creates a greater distance here between the mineral sheets. Illite is a non-swelling mineral, and I want to show that when mica weathers, it can create a mineral like this, where you can see that we have vermiculite. We can have a layer of vermiculite here, and right below it a layer of illite, and right below that a layer of another smectite, montmorillonite, and so on. And the idea here is that these changes in minerals can occur in very short distances, and these are very common in soils. In fact, more common than just the pure minerals themselves. So we call these interlayered or interstratified minerals, and typically you'll see that illite and smectite are often interlayered with one another over very short distances, and this affects the way the potassium reacts in these soils. Here's a transmission electron micrograph of these minerals, and the important thing here I just want to point out is when we look at these TEM images, these individual lines here are the actual edges of individual sheets in the mineral layers, and you can see that there are places, for instance on the right here, where we can get greater and greater spacing between these individual layers near the edges, creating like a feathering where we see that these layers are breaking apart, and that creates highly reactive surfaces for us. And so I just wanted to show you actual images of some of these minerals to show you how varied they can be across very short distances, and how those distances between the layers can be highly varied. One of the things that is very important for us in the reaction of potassium in soils is how much water is present, and that affects the charge of iron in these minerals. Minerals like smectite and illite have iron substituted in for aluminum in that middle octahedral layer, and that iron can take on two different charge states. One of it is a 2+ state, and that usually occurs under wetter conditions in soils. As soils dry and more oxygen is present, that iron can change its charge state from a 2+ to a 3+, and that can drastically affect how much K is fixed by individual soil minerals. So I have two examples of a smectite mineral, and I have one example of an illite. And what I'd like to point out is just how differently K reacts under the same conditions in the two minerals. So here we have the two smectites. We can see that when we go from an oxidized or an unreduced state to a reduced state, we increase the amount of iron in the 2+ state. And that affects how much K is fixed. We can go from very little K fixed to a substantially greater amount for both smectites when they are under reduced or waterlogged conditions. The illite, on the other hand, under those same conditions, where it now has more structural iron that's in the 2+ state as well, it actually fixes less K, or it releases K under those waterlogged or moist conditions instead of fixing it. So the idea here is that smectites and illites behave very differently when exposed to different chemical conditions. When soils are wet, smectites tend to fix K, and illites do just the opposite. They tend to release K. So just a little bit more here before we break for questions. Here's some data that was produced many years ago, but illustrates the importance of these differences between illite and montmorillonite. Here we have soil moisture on the x-axis, and we're going to show what happens when samples are dried in the laboratory. This is, for instance, drying a sample before analysis, which is typically done. And here we'll have a sample where no potassium was added to the sample prior to drying. You can see that as the soil moisture decreases, the soil test K of the sample increases. And what's happening is as the sample is dried, K is released. So this behaves like smectite. Now, if we add K to that same sample, that same soil, and then dry it, we see just the opposite behavior. So where we've added K, now when we dry it, the sample actually fixes K. So this is for the same exact soil. So this tells us, or at least indicates to us, that adding potassium to a soil could change the behavior of that soil. Where we've added K, its behavior is more like illite, and where we did not add K, the behavior was more like smectite. So some further evidence of this has now come very recently. And if you'll bear with me for just a minute or two, I'm going to go through a little bit of technical information on an X-ray diffractogram. This is a technique that soil scientists use to try to identify what minerals are present in a soil. And I'm going to show how this diffractogram can be analyzed using some software to discover how much relatively of each mineral may be present. And this is an important part of discovering what the impacts of potassium are on the mineralogy. So here we're just going to give you the basics of a diffractogram. Here we have the angle that the radiation is hitting the sample at, and then we're seeing the intensity of the reflected radiation. And here's just an example of the kind of diffractogram that you might get from a sample. Now, how would you interpret this? Well, we have software that will take what is known about certain minerals and apply that knowledge to decompose this graph. So, for instance, this software would come in and say, okay, part of this peak here can be accounted for by a smectite-rich mixed layer mineral. This other little peak here can be decomposed into a hydroxy interlayered phase. So we keep going and we look at other minerals that may be possible. Here we get to an illite-rich mixed layer mineral, a poorly crystallized illite, and then a well-crystallized illite. So all these peaks added together can reproduce this spectrum. Now, the important thing here is as we go from the left side to the right side, you notice that these numbers, which represent the spaces between the individual mineral layers, decreases. So here, the larger spacing means that we have more space between layers, and the smaller spacing means that we have less space between layers. So if we can just look at the spectrum and do a weighted average, we can come up with some sort of a concept that's called the center of gravity. So this is just an area-weighted average of these spacings. And so I'll show how this can be applied to the potassium problem. Here was a study that was done for 40 years, and it was looking at potassium budgets, and here are the treatments. No potassium applied, just phosphorus applied, only potassium applied, both potassium and phosphorus applied, no P or K initially, and a dose of P and K initially, followed by no doses later. Here's the total amount applied over the 40 years. Here's the total amount removed, and you can see the net addition or removal. So where we have negative numbers, that means that we've had a net withdrawal of potassium. Where we have the positive numbers, that means we've had a net addition of potassium. Now, they've taken those budgets and plotted those against that center of gravity that they got, that these scientists measured with the X-ray diffractogram. And you can see that where we had negative budgets, our center of gravity tended to be higher. That means that there was more space between the individual mineral layers, meaning they behave more like smectites. As we added K, there was less space between the mineral layers, and they behaved more like illites. So this is kind of an important finding, is that adding potassium to soils or enriching those soils with potassium, which can also come with natural processes, which I'll show later, can influence the behavior of those soils and change a bit their mineralogical characteristics. So in summary, to this point, we've seen that pure mineral phases are not common, that interstratification on very small scales is common, and that there's some evidence that K enrichment may cause some mineralogical changes. So with that, I think I will take a short break, and I guess, Eros, I will turn it back over to you to see if there are any questions to this point.
All right, Scott, thank you for this first half of the presentation. Very interesting. I would like to mention to all the audience that I forgot to say that IPNI is developing these webinar activities, and in some cases the activities will be aimed to a public with practical solutions. In other cases, as like this one, we want to spread scientific knowledge and also give the opportunity to everyone that works in the chain of agriculture to interact with the knowledge, if it is more practical or basic, like the scientific one that we have the chance to see today. So far, I don't see any questions in my screen that you may have typed. If you do have a question, please feel free to type your question in. You just have the webinar tool available in your screen. You just type your question in the question short window. We can wait a few minutes if you want to make any questions so far. If not, go ahead, Scott.
Oh, I think, Eros, if there's no questions, I think I'll just proceed and we can kind of show the rest of the presentation how some of this mineralogy affects some very practical things that we're doing with potassium recommendations. So.
Okay, and then we let the questions to the end. We leave the questions to the end. Okay.
Okay, very good. Okay, well, I appreciate your patience with some of the more technical information. What I'd like to move to now is how that mineralogy affects the two things that we're most concerned with. How accurately we can assess potassium soil fertility using soil testing methods. And after this section, I'll go into how mineralogy affects our ability to understand the impact of our nutrient budgets. So both highly significant things for farmers and advisors. So the first one is looking at how this mineralogy may be affecting our ability to assess soil potassium requirements. In the past, when we take a soil sample, our most common method of preparing that sample is what we have termed the dry method, and that is that a sample is dried, usually either just in the air, open air, or in an oven at temperatures less than 40 degrees C typically. After that sample is dried, it is then crushed and sieved, and then a subsample is taken for analysis. Back in the 1960s and the 1970s, there was another method of preparing soils that was called the wet method. It was used almost exclusively in the state of Iowa. That test was not very practical, or that preparation was not very practical. It was more time-consuming. But it has now gotten more attention, and I'll show you why. In the wet method, instead of drying the sample as it came from the field was directly sieved, and then a subsample of that sieved wet soil was taken to determine the moisture of it, and then based on that moisture, a 2-gram equivalent sample was then taken for analysis. So with a wet method, we skip this drying step. And as you can see from the previous discussion, that drying can drastically affect how much K is released or fixed prior to analysis based on how much potassium that soil has in it, among other things. So by skipping this drying step, the idea is to get rid of a major source of variation in our soil test procedures. So this is beginning to receive more attention again. I'm going to show you the difference, some recent data that shows the difference that we get between this dry conventional method of preparation and this wet method of preparation. The graph that I have here is really the basis of all of our potassium recommendations, these types of graphs. These are what we call soil test calibration relationships, and they help us understand how unfertilized soils can yield compared to fertilized soils at various soil test levels. And the importance of this is that it shows us what the yield loss and potentially is at lower soil test levels, and what the probability of the response to fertilizer may be. So here we're looking at relative yield, and this is just the ratio of unfertilized soil to fertilized soil. So you can see here when we get to lower soil tests, if our soils are unfertilized, we can yield much less. In some cases, we yield only 60% of what would be possible if we fertilize those soils. You can see that the researcher here, Antonio Mallarino, was trying to do some work to understand how this variability was composed. And he looked at various drainage levels of the soil. We have poor, moderate, and good. And you can see that the poorly drained soils were some of the most responsive soils to fertilization, had some of the lowest yields if they were left unfertilized. Where we had good drainage, yields, if unfertilized, were not that bad. So there may be something that we can do to improve our overall site-specific management of potassium. But right now, I think our knowledge is not enough. And so what we do as scientists is we group all of these data together from as many sites as we can to come up with these general relationships. And this is based on the dry test. And you'll notice how much variation there is among those points. It's a true cloud. But there is some relationship here with lower tests and lower yields. If we look at the wet test, these are the same soils just with a wet preparation rather than a dry preparation, and that's what this graph is. And you can see here that there's much less scatter. And so the idea that a moist method helps to reduce some of the variability in soil testing, I think that hypothesis has been validated. It does look like that keeping soils moist prior to analysis does eliminate some variability in our interpretation of those tests. So this has become an important issue in the U.S. Midwest, is locating labs that are willing to do this wet method of preparation, and labs themselves are trying to think through the logistics of creating this wet preparation method as an option for their customers. And so all of this is part of what's happening right now in my area. One of the things that, and you could probably anticipate this from our earlier discussion, but the difference between the dry and the moist preparation differs with soil test level. What I'm showing here is that in this graph is as we at the lower soil test K levels, the dry, if we look at the dry to moist ratio, the dry test produces much higher values as soil testing results than does the wet method of preparation. As we get to higher soil test levels, the differences between the two methods of preparations becomes insignificant. So it again shows the importance of potassium fertilization on the mineralogy and the behavior of those soils under laboratory conditions during soil testing. There's also work that has been done, instead of trying to get a lot of different data from a lot of different sites. There's some work done by Purdue University in Indiana that is trying to look at how site-specific these soil test calibration relationships are. And there, I'll show you a few findings. This is from one of the long-term study locations in central Indiana. This is on a silt loam soil. And you can see the calibration relationship. It's a bit different analysis, but you can see that there is some indication that at lower soil test K levels, there are some yield reductions. And this is at one site over many years. Here's a separate site that is a sand. And you'll notice that there's very little reduction of yield at low soil test levels, which is surprising because it's a sand. So many soil scientists, I think, and practitioners and farmers feel that sands in general do not have many nutrients to contribute to crop production. However, there are some examples like this one and also a few other examples from Nebraska and some states to the west where it's drier, that sands can sometimes produce enough potassium to feed the crops their requirement. And part of the reason may be that sands themselves can have some of these layer silicates in them. Here's some new, a relatively new study that just looked at a new technique, a new analytical technique that allows us to map soil minerals at a very small scale. So these pink blobs are actually individual sand grains. And this chemical mapping technique allows us to understand how the minerals change over that individual grain of sand. And what I'd like to show here is that there are some feldspars, which are potassium-bearing minerals, within the sand grain. Sand is not just quartz, as we often think of it. There are some other minerals present. And here the red is very interesting because that's actually a mica. And that is a phyllosilicate that we often think only occurs in that clay or the very small size fraction. So some of these new techniques are helping us understand that these larger size fractions, which we often think are just quartz, can contain other minerals, some of which are these layer silicates that are very important to potassium reactions. So I think in the future we'll need to look at some of these larger size fractions instead of just the clay size fractions to try to identify which sites may respond to potassium fertilization and which ones won't. So this has been some very interesting information that has shown that some sands may contain enough potassium, and that certainly has been confirmed with some studies that have shown some sands to be very unresponsive to potassium fertilization, which you would not think just based on texture. So to summarize this small section, the wet method of preparation, I think, does decrease the variability in our results and helps us do a better job of interpreting what we get from soil testing. Those differences tend to be greater when the soil test levels are lower, and as soil tests increase, then the differences between the dry and the moist tests seem to go down. They become essentially the same. The work from Purdue shows that different sites can have different critical levels, different levels at which the soil is sufficient in potassium, and different levels of crop responsiveness. And some of the new studies are showing that these layer silicates that we often think are only in the clay size fraction can be in larger fractions and help us. That knowledge may help us do a better job of anticipating potassium responsiveness across different soils. Okay, I'll look at the last issue that we have then, and that is how can mineralogy help us understand and interpret how soils respond to K additions or K withdrawals. Again, this is really coming from our crop advisors. They are often very frustrated that when they apply potassium to try to build the soil tests, that the soil tests do not respond in the way that they expect. And so I'd like to take a look at some of those issues that they face. Here's a study that was done from Illinois. This is from the U.S. Midwest. And here we are just looking at one soil with no change in management, just sampled intensively over time. And these black circles are the soil test K levels across 1994, 1995, 1996, and 1997, sampled approximately once every month. And here we have the first letter of the month names. In English, this would be starting in June, July, and August, September, October, November, and December. So this is starting in the fall of 1994, then going through the winter, January, February, March, April, May, and through the rest of the year, another whole year, and then through the spring of 1997 through January, February, March, and April. And here you can see the black dots are the soil test K, and you can see how much that varies over time with no change in management. And so we can go, levels can go from 140 parts per million down to 80 parts per million, and they fluctuate over time. The other thing that we have plotted here is soil moisture. And you can see that in general, when the soils get drier at this location, the soil test potassium level also went down, or the soil test K reading, I'm sorry. As the moisture level increased, soil test K results increased, became greater. So there was a direct association between soil moisture and soil test K, but the soil moisture did not explain all changes in soil test K. There were instances where the moisture increased and the soil test K level decreased. So it doesn't explain everything, but we think that the soil moisture is very important for helping interpret some of this seasonal variability in soil test K. So here is a kind of a problem that our crop advisors face often. This is a study that was done in Iowa over 15 years. This was a maize soybean rotation. And here we look at the cumulative amount of K removed over that 15-year period. And that's what these black diamonds are showing. So by the end of the 15th year in this rotation, the total amount of K removed was approximately 600 kilograms of K per hectare. Now, these gray boxes indicate how the soil test K decrease. It's not the actual soil test K level, it's the decrease in soil test K. You can see that that decrease varied a lot over time, and in some cases it was greater, some cases it became less again. So you can imagine that if you're advising a farmer and you start out initially and say, okay, our cumulative or our soils are good, let's not fertilize for 2 or 3 years, and we should see a decrease. Well, farmers don't sample soils every year, they sample soils every 3 or 4 years, and you can see that if we had started out advising a farmer here and came back and sampled the soil 3 years later and had sampled this point, we would find that the soil test K level had changed very little, even though we expected it to change much more. So this has been frustrating to crop advisors, this kind of variability in soil test changes. And so they are asking scientists to try to help them understand and manage that variability and do a better job of assessing soil test K. One of the key things that we deal with that all of us experience is nutrient uplift. And this affects very much how much K we measure in a soil sample. Our samples are typically taken to 15 centimeters deep. And the plants themselves will recycle K from the lower part of the profile to the surface. And that can enrich the surface and keep our soil test K readings elevated with our shallow samples. So to demonstrate the uplift, here I'm showing a soybean plant with a banded K application. During the plant's life, it takes K up from that band and redistributes it to the aerial portions of the plant. When that plant begins to die, then the K is leached out of the plant tissue and is deposited at the soil surface. And so this uplift is the movement by the plant of K from the lower part of the soil profile to the surface. And that creates an enrichment of K at the surface. And as we showed earlier in this presentation, that can affect how much illite is present. It could increase the illite content of the soils here relative to the montmorillonite content. And we'll show some implications of that. Here's one of the key, and this is I think my last graph, this is a key question that we get from advisors, is how much potassium does it take to increase the soil test levels by 1 part per million? And if I'm withdrawing potassium from the soil, how much potassium does it take to draw down the soil by 1 part per million? This study showed that the two are not the same. It showed that if we have a net addition of potassium to the soil where we're trying to build up the levels, it takes, and I'm sorry these are in English units, but it's the relative comparison that's important. This is 4 pounds of K2O per acre to build the soil test 1 part per million. If we are drawing it down, it takes almost twice that amount. We have to withdraw almost twice the amount of K to decrease the soil test by 1 part per million. And one reason, one possible interpretation of why there are these kinds of differences is think about that uplift that we just talked about, how the plant moves potassium from the lower part of the soil profile to the soil surface. And the soil surface is where we take the soil sample. If we add K to the surface of the soil, and the plant is also adding K to the surface of the soil, those two are working together and moving soil test K in the same direction. They're both increasing soil test K as we measure it at the surface. However, if we look at withdrawing K, in this case, as we remove more and more K from the soil test, or the actual amount of K in the soil is going to be decreasing. But the plant is recycling the K from the lower part of the profile to the surface, and that can enrich the surface where we're sampling. So in that case, our K budget and our K uplift are not moving in the same direction. They're moving in opposite directions. The plant is enriching the soil surface, but our overall withdrawal of K is removing K from the soil. And so it may, because of this uplift, we may have to withdraw more and more K from the soil before we begin to see a decrease in the soil test level as we measure it. Okay, so to end then with this last slide, this is to provide us with just a few gaps, a few of the many gaps that we have in our understanding. The first is, to what extent are the mineralogical changes that we're seeing, that when we add K, that we could be shifting some of the mineralogy in the soils? How is that affecting both the accuracy and the precision of our soil testing methods? Can we do a better job of incorporating these mineralogical factors into our soil test interpretations? As we showed earlier, the recommendations that we use in the U.S. do not really consider mineralogy much at all, only really with cation exchange capacity. And is there some relationship here between our dry to moist ratio and the critical level, the level that we would think that soils, we would interpret those soils to have an adequate supply? Maybe there's something there that might help us. Maybe there's some sort of equilibrium that exists If we could understand that, maybe we can do a better job of coming up with site-specific critical levels for various soils. So that's all under evaluation. And the last is under our control. How do we manage potassium to change soils in the way that we want them to change? And I think we still have quite a bit to learn there. Our soil tests as we receive them are still very variable. And when we expect the soil tests to increase, sometimes they do, sometimes they don't. When we expect the soil tests to decrease, sometimes they do, sometimes they don't. It's very hard to come up with evaluations of management when the tests that we use to evaluate that management are so variable. Okay, with that, I think I will stop and entertain any questions that may come.
Thank you again, Dr. Scott, for this very interesting presentation. We do have a couple questions, and I will start with the first question that came right at the end of our break, but I had passed the word to Dr. Scott, so I decided to move it to the end. But Scott, as you have the questions available in your screen, you may read them if you want, but I will read for the audience too. So the first one comes from Mr. Azu, and he wonders, how does the change in mineralogical behavior of the soil when you add potassium can change the effect of the soil to retain or provide water to the plant?
Yeah, I'm sorry, Eros, could you please repeat that again? I'm trying to find the question as well.
The first question concerns about if you add potassium to the soil, you may change the mineralogical behavior of the soil.
Yes.
And how does that affect the ability of the water to release or retain water to the plant?
Yeah, I think so far we don't really have a good understanding of that. There is water if we, for instance, if we are adding potassium and we create something that's more illite-like in behavior, that will not have water in the inner layers between the individual clay mineral layers. If we are withdrawing potassium, we would expect some shift towards smectite that does have water in the inner layers. I don't think, at least I haven't seen any research that shows that those mineralogical changes affect the availability of water to the plant itself. That may be. I just haven't seen the research on that. The most effect is going to be on the potassium availability. So I guess at this point I'd have to say that I'm not aware of any differences in availability of water.
Okay. Thank you. So the second question comes from Dr. Luis Proshnov, and it says, would you expect changes in behavior from what was presented for tropical soils, more like one-to-one clay mineralogy or iron aluminum oxides?
Yeah, that's a good question. And the one-to-one clay minerals, they're not going to have the same kinds of changes that I just talked about. They're non-expansible, and without they have different charge characteristics. So potassium binds primarily on the edges of those minerals and on the surfaces. So the inner layer movement of potassium that is characteristic of montmorillonites and illites would not be the case for kaolinites with a one-to-one clay mineralogy.
Okay. The next question comes from Mr. Ubiera, and it says, what importance do you assign to soil K saturation, percentage of potassium in the CEC, to interpret soil K availability?
Yeah, I guess K saturation, that is important. There has not been a lot of trying to relate that to CEC as kind of a percent base saturation, if you will, or a percent K saturation. We've not done a lot of that work in the U.S. There has been some work done on the east coast of the U.S. where the soils are very coarse, and there has been some relationship in very coarse textured soils between K saturation and K availability. In our silt loam soils with a lot of 2-to-1 type clays, I don't think there's been very good relationship shown between K saturation and soil K availability. And in terms of acid soils and high pH soils, we just don't have the data to be able to make that fine differentiation for those situations.
Okay, thank you. We do have time for one more question before we end. And I'm sorry, this again from Dr. Luis Proshnov. What are, in your opinion, the most important topics for research related to K nowadays?
Yeah, that's a really good question, and one that gets really to the primary questions that we're trying to answer. In his book, Soil Fertility Evaluation and Control, Dr. Black from Iowa State elaborated the entire problem of soil testing into 2 basic categories. We have to be able to evaluate soil fertility in some way. We have to know whether or not soils have an adequate supply or not. Once we have some evaluation of that fertility, then we have to control that fertility through management, either increasing it or decreasing it or keeping it the same. And it's a very nice categorization of our total problems that we have. Right now we have problems in both major categories. We're not sure that we can properly evaluate soil fertility based on our current soil testing methods. They work to some degree, but they are very coarse in their resolution. Without properly evaluating the potassium status of our soils, we have problems controlling it through management. This is another area that we struggle with. We need to be able to come up with some way of being able to directly see the impacts of our K management on soil fertility. So we have problems in both areas, and these 2 major topics, the soil fertility evaluation, the soil fertility control through management, it's unfortunate. These are very basic things, but I think these are our most important topics. Mineralogy is important, but there are so many other aspects to potassium management that are important as well. We have the soil biology. There are bacteria. I didn't get into this, but there are bacteria that affect the behavior of minerals and the release of K. The plants themselves have very different abilities to access K based on the types of reactions that occur right in that soil zone, right around the root. So there are many soil issues. There are many plant-soil interaction issues. And then plants themselves with new genetics and greater yield potential, all of those things really have to be considered. So I wish I could limit it to a few key things, but there are many things that we need to consider right now, encompassing the entire soil plant system.
Okay, thank you again. Well, we do have a couple questions and one comment, but due to the time, we do have to end this question, so I will share the questions with Dr. Scott, and we may go ahead and provide some answers to them. I would like very much to, on behalf of IPNI Brasil program, thank Dr. Scott for his participation and his time in providing this presentation for us, a very, very nice and interesting presentation. I have no doubts that this presentation brought insights to many of the people in the audience, and I would like to also say again that this is a scientific webinar that IPNI Brasil program is developing. It differs a little bit from the extension webinar that we also run once in a while. The focus of this scientific webinar is the academic public, people from the university, people from research institutions. And I apologize for that. And the extension webinars are focusing on a public that direct deals with the applied decision, like agronomists, ag consultants, farmers. So we appreciate you all, the audience, being with us for this hour, and stay focused with the IPNI website. We will develop more of these activities in the near future. I thank you so much, Dr. Scott, again, and hope you have a nice week. And I don't know if you want to say something.
Oh, no, thank you, Eros. Again, I very much appreciate the attendees tuning in today and listening, and thank you, Eros, so much for your arranging this webinar and making these available in Brazil. I very much appreciate that.
Okay, so we come to the end. I thank you all and hope you have a nice week, everyone. Bye-bye.